Howdy, my name is MiaCarolla, and I am a third-year PhD student in Materials Science and Engineering at Texas A&M University, focusing on additive manufacturing of polymer composites. So over the past decade, carbon fiber composites have exponentially increased in popularity, and not just because they look sleek in high-end sports cars. Carbon fiber composites are an essential part of the automotive and aerospace industries because they are a lightweight alternative option to aluminum and steel. Carbon fiber composites are very high strength for a fraction of the weight of their metallic counterparts, which makes them a very attractive option for these industries. Though the popularity of these materials has increased, the manufacturing methods and materials that go along with them haven't really evolved over the past few years. So when you consider traditional manufacturing methods such as resin transfer molding of your composite parts, you're up against very timely processes. They're very cost ineffective, and they don't give you very much ability to have flexibility in your manufacturing because of the tooling that's required for each specific part. This creates a big opportunity space for a new manufacturing method, such as additive manufacturing, to step in and even bring in new materials such as high-performance thermoplastics into the equation. When you think about additive manufacturing, and specifically in my work, fused filament fabrication, you can eliminate a lot of the timeliness that comes with your traditional manufacturing methods. You have a lot of flexibility with your design, and you're eliminating all of that bulky tooling that can be very costly. Fused filament fabrication utilizes thermoplastic filaments that are extruded from a print head in a layer-by-layer process, and this processing can really bring composites into the 21st century. When we consider putting these two technologies together, the carbon fiber composite and the additive manufacturing methods, we can really evaluate them in three stages: before, during, and after printing. Before printing, we want to evaluate the interface between the carbon fiber itself and the thermoplastic matrix. If the interface is weak between these two materials, you'll see that magnified in the printing itself. And what will often happen is you'll see delamination or fiber pullout in the final printed product, which will result in failure ultimately. In order to remedy this interface being problematic, we can use a couple of different strategies. The first is to apply sizing or a type of coating to the carbon fiber to increase the bonding between the two materials. We can also incorporate nanoparticles such as graphene nanoplatelets or carbon nanotubes in order to facilitate that interface being stronger. During printing, we're more concerned with the morphology and the crystallinity of the material as it's being extruded from the print head and then as it's cooling directly after extrusion. The crystallinity behavior is also going to be altered by any nanoparticles that you employ. These will act as nucleation sites for these crystallites, changing the overall crystallinity and therefore the mechanical properties. After printing, we will explicitly look at these mechanical properties in a more holistic sense, so that way we can compare to and even substitute those composites manufactured using traditional methods. This will also allow us to tailor and optimize the previous two stages of processing to get optimized properties. Thank you for your attention, and I hope to have piqued your interest in composites beyond just the aesthetically pleasing interior of sports cars. Thank you.